Welcome to General Chemistry Mini Lecture Series, Lecture 26, Temperature, Heat, and Heat Capacity. Temperature describes how energetic each particle is. And temperature does not depend on sample size, so therefore temperature is intensive property. Let's take a look at two samples of water. One is one glass of water, another one is a pool of water. And they both are the same temperature, let's say 25 degrees Celsius. Okay, so the temperature is the same. Does not depend on the mass or how much water you have. You see? So if you have a pool of water, it's 25 degrees Celsius. If it's glass of water, 25 degrees Celsius. Heat describes how much energy that is in the whole sample. Obviously here, this whole sample, this is a much larger sample and this is a much smaller sample. Heat doesn't depend on the sample size. So therefore heat is extensive property, while temperature is intensive property. Make sure you understand the difference. And we can further understand what's going on right here. For example, if you heat this glass of water to 26 degrees Celsius from 25 degrees Celsius, which means increase the temperature by 1 degree Celsius, it would require about 3 kilojoules. Compare with increase the temperature of this pool of water also to 26 degrees Celsius from 25 degrees Celsius. That means increase the temperature also by just 1 degree. Look at this. It would require 300 million kilowatts. So therefore, heat is extensive property and temperature is intensive property. Heat capacity. So when a system absorbs heat, the increase in temperature is directly proportional to the amount of heat absorbed. So the proportionality constant is called the heat capacity. Q equals heat capacity times delta T. Delta T is the temperature change. Heat capacity is the ratio of heat absorbed to the temperature change. Therefore, the unit for heat capacity has to be joules over temperature, whether it's in degrees Celsius or in Kelvin. Temperature change, final temperature subtracted by initial temperature, that's delta T. And of course, we can also calculate the delta T from this key equation. Delta T equals Q over C, just like here. This is a key equation. From this key equation, you should be able to write this equation for calculating heat capacity or this equation for calculating the delta T. Let's work on this example. A piece of iron metal absorbs 15.3 kilojoules of heat while its temperature rises from 22 to 962 degrees Celsius. Calculate the heat capacity of this piece of iron metal. Recall the key equation. Heat equals heat capacity multiplied by the temperature change. And now, from this key equation, we should be able to write down the heat capacities equation that can be calculated by using heat. Do we know heat? Yes, it's right here. Do we know temperature change? Not directly, but the temperature change can be calculated. All right? So therefore, we just use the heat, 15.3 kilojoules, and I want to convert from kilojoules to joules, because in the heat capacity, we are going to express that in joules per degree Celsius. Okay, so therefore kilojoules are cancelled, and now the temperature change, final temperature subtracted by the initial temperature, and now we have 16.3 joules per degree Celsius. Let's take a look at specific heat capacity. That's heat energy required to raise the temperature of 1 gram of substance by 1 degree Celsius or 1 degree Kelvin. Let's look at the key equation right here. In this case, the heat, or Q, can be calculated by the mass, then multiplied by specific heat capacity, not just C anymore, but Cs. C is just heat capacity. Cs is specific heat capacity, then times temperature change. Now the units for specific heat capacity should be joules over gram and degree Celsius or gram degree Kelvin. Molar heat capacity, Cn, that's simply the amount of heat energy required to raise the temperature of 1 mole of a substance by 1 degree Celsius or 1 degree Kelvin. That's the molar heat capacity that can be calculated using the number of moles multiplied by the molar heat capacity Cn multiplied by the temperature change. Let's work on one example. The specific heat capacity of copper is 0.385 joules per gram degree Celsius. A. What quantity of heat is transferred when a piece of copper wire, 200 grams, cools from 105 to 5 degrees Celsius using liquid nitrogen? B. What is the direction of flow? Let's work on A first. This is the key equation involving specific heat capacity, and that can be used to solve this problem. Heat can be calculated by the mass, 200 grams, multiplied by the specific heat capacity, that is given 0.385, multiplied by the temperature change, final temperature, subtracted by the initial temperature, that should be 100. And then we have negative 7,700 joules, or you can convert that to negative 7.7 kilojoules. This simply means the heat transferred is 7.7 kilojoules, and the negative sign means this is an exothermic process. The direction of the heat flow, since it's an exothermic process, then heat must be flowing from the system to surroundings. And the system in this question is copper, and the surrounding in this question is nitrogen. Okay, I would like to make a comment right here. This is the key equation for this problem. And in this question, we ask you to find out, you are asked to find out the heat required. But if other of those parameters are asked, you need to be able to find out the equation for solving each of these three here. So that brings up from this key equation to these three secondary equations. If you need to calculate the mass, you have to be able to write M equals Q divided by move Cs and delta E to the other side as a denominator. Do the same for solving for Cs and for delta T. Delta T can also be calculated by using this equation, initial final temperature subtracted by the initial temperature. But sometimes you are asked to find out the final temperature or initial temperature. So therefore, from this key equation, you have to be able to write the equations for solving for TF and TI using simple math skills. Let's take a look at this example. The specific heat capacity of water is 4.18 joules per Kelvin. What is the molar heat capacity of water? First, we need to find out the heat required for raising the temperature of 1 mole of water by 1 degree. Celsius. 1 mole of water, we convert that to grams using molar mass, and we have 18.02 grams. Next, we are going to use this equation to find out the heat required for heating 1 mole of water. We just obtain the mass for 1 mole of water, and this is the specific heat capacity of water, and the temperature change is just simply 1 degree C or Kelvin. So therefore, the heat required for heating 1 mole of water by 1 degree is 75.32 joules. Now we are ready to find out the molar heat capacity of water. From this key equation, we want to find out the molar heat capacity, which is Cn. We have to write down the equation for solving Cn. We simply move N and delta T to the other side as a denominator. This is the equation we need for solving this problem. Q, we just calculated from here, from the previous step. And then N is 1 because the molar heat capacity, based on the definition, is the heat required for heating 1 mole of the substance by 1 degree. Temperature change, of course, is 1 degree K. So therefore, 75.32 joules per mole per Kelvin. That's the answer for this question. Here are the first 3 quiz questions for lecture 26. Let's work on question number 3 together. When 111 grams of water at 22.5 degrees Celsius is cooled by the removal of 525 joules of heat, what is the final temperature of water? Specific heat capacity of water is given right here. Obviously, we need to recall this key equation. So from this key equation, we should be able to write down the relevant equation of calculating delta T equals Q over M and Cs. Then what is the Q? In the question, 525 joules of heat is removed from the system, from water. Okay, so if it's removed, which means giving off heat, that should be negative sign. So therefore, that's negative 525 joules. The mass, 111 grams, and the specific heat capacity, 4.18. That should give us negative 1.13 degrees Celsius. Okay, we have another key equation for calculating delta T though. Delta T equals Tf minus Ti. And from this key equation, delta T key equation, we should be able to find out Tf equals delta T plus Ti. And then delta T is negative 1.13, and Ti, the initial temperature of water, is 22.5. And that should give us, after taking care of the sig figs, that should be 21.4 degrees Celsius, and C should be the correct answer. You guys can work on question number 4. And this is lecture 26. I will see you guys in lecture 27.